Hello, good morning. How's everybody? My name is Terrence Barkin. I'm the Executive Director of the Graphene Council, and we're going to share a presentation with you today about the results of a comparative study in a two-part epoxy system. Jason Gibson is next to me here from Composites 1, and he'll be taking over most of this presentation after we give you just a short overview of who we are. So the Graphene Council is represented here today. Vibrance Technologies. You'll hear from Paul Redinger. He's not able to be here, so there will be a recording, but that's a small part of the presentation. And then, of course, Jason will be speaking. So if you're not familiar with who the Graphene Council is, the Graphene Council is a trade and professional body that represents the graphene sector. And this includes graphene producers as well as graphene users. If you've not heard of graphene, and I assume you have, one of the reasons why it's so exciting is because it can be used in so many different applications. And one of the main applications that it's used in is in composites. Now, there are different types of graphene material. When you hear this, you only hear graphene, and it would be easy to assume that graphene is one material, but it's really more like a family of materials that can be used in composites, elastomers, coatings, all sorts of applications. But it's important to get the right kind or morphology of material for the application that you want to use. And so we have things like a graphene oxide, which has about 30–35% oxygen in it, a reduced graphene oxide, a functionalized graphene material, etc. So one of the things that we wanted to achieve with the study that we did, we took multiple forms of graphene materials, more than 15 of them, and did a head-to-head comparative test to see how they would work in a two-part epoxy system. And the role of the Graphene Council in this, because we're independent, we don't sell graphene, we don't make graphene, but we represent that sector, is we wanted to act as a project manager for this testing project, give it independent third-party analysis. The samples that were received from our member companies were blinded so that the companies that were involved in doing the master batching and putting the testing coupons together, which was done at the University of Maine's Advanced Composites Center, did not know which material was being used. So it was this blind testing. And the other thing to remember when you see these results, to put them in perspective, these were non-optimized. So we took the sample materials, which included functionalized, non-functionalized, graphene nanoplatelets, etc. And we did exactly the same test protocol for all of the materials, making a master batch, then letting it down into a resin system, making the test coupons, and then doing physical testing for those test coupons. And what you're going to see next is an explanation of how that process was administered, and more importantly, you're going to see what kind of results were received from that testing.
Hi there, my name is Paul Redinger, and I am a technical manager leading research and development from the Color Solutions Group in nanotechnologies for a company called Vibrance Technologies. Vibrance Technology was formed a year ago from the merger of three different companies, Chromaflow Technologies, Ferro, and Prince Industries. Our purpose is to bring color, vibrance, performance, and vibrancy to life. Our vision is to be an enduring world-class specialty chemicals and materials company, and our values are safety, commitment to customers, our people, sustainability, environment, commitment to excellence, and of course you can't have any of these without integrity, ethics, and trust. Vibrance Technologies is divided into three business segments. The Advanced Materials Group makes manganese, specialty chemicals, and advanced battery materials for battery applications, electronics, and electronic surface finishing. Our Color Solutions groups make pigments, specialty chemicals, specialty pigments, and additives and chemical dispersions for specialty chemical industry. We also make performance coatings for industrial and porcelain and enamel applications, and also for decorative, industrial, and automotive glass coatings. One might ask, what does Vibrance Technologies have to do with graphene? Well, as a matter of fact, it's been an area of intensive applied research for the past decade. We don't make graphene, but our Color Solutions group has been dispersing carbonaceous nanoparticles for 25 or more years. So we do disperse graphene, and we continue to experiment with ways of customizing nanoparticles, including graphene, for specific applications, including but not limited to transportation applications, electrical, battery, coatings, and many other applications. As relates to the Graphene Council project, with the University of Maine, the Graphene Council, Composites 1, we at Vibrance Technologies received 19 encoded graphene samples. This was a blind study. We didn't know the identification of each of the materials. We did notice, however, that they were somewhat different from each other. And so our job was to process the samples into stable, rheologically consistent, but processable liquid master batches in a bisphenol F resin of approximately 3,000 centipoise. We took significant steps to ensure in the process of dispersing these that two-dimensional nanoparticles were deglomerated, deflocculated, but otherwise undamaged and not disturbed by our dispersion process. And so the specific loadings of graphene varied according to the surface area of the samples we received. There were some samples that were we could only get maybe 1 or 2% of graphene into it before the viscosity would have been unprocessable for the University of Maine to handle. And there are other samples that we could go as high as 20 or even 25%. So we processed them into a manner that was rheologically consistent, stable, and also handleable by the University of Maine. And when we accomplished that task, we shipped them to the University of Maine for further testing. At the University of Maine, the samples were let down to 0.1 and 0.5% loading in epoxy resin based upon weight. The samples were then mixed using a high-speed orbital mixer and degassed under vacuum. A curative package was then introduced, and in the curative package, we used a common amine ratio for all samples. We did not adjust stoichiometry to account for potential functionality in graphene itself. We wanted to keep all things the same and treat all samples exactly identically. This is both a strength and a weakness of the study. We then mixed the samples, poured them onto molds on 60 degrees Celsius, and cured them for 1 hour. The samples were then subjected to a 3-hour post-cure at 160 degrees Celsius. From the resulting panels, we then cut specimens from the molded panels, subjected them to flexural, instron, and notched IZOD testing. In general, performance varied significantly, but we did see a number of samples that exhibited gains. In some cases, we saw as high as 30 to 35% gain in flexural strength, and we saw between 70 to 75% gain in flexural modulus. What is also interesting is that there were a few samples that, in spite of significant gains in modulus and stiffness, it did not adversely affect the notched IZOD values resulting from embrittlement. Dr. Jason Gibson will update you on the specific mechanical property results.
So good morning. My name is Jason Gibson. I'm the Chief Applications Engineer for Composites 1. I've worked in composites for over 20 years, and 17 of those have been with Composites 1. So I've been tasked with presenting the results today, but before I do that, I want to just take one slide and give you a brief introduction of Composites 1. So Composites 1 is the largest composite-focused material management company in North America. On any given day, we're supporting our customers by providing over 40,000 unique products from over 600 suppliers. But the key to remember about Composites 1 is that our strength lies in being able to sit down with our customers and understand their unique challenges and situations and look across that broad portfolio of products to develop a unique, comprehensive solution for their specific needs. And that partnership with our customers goes beyond simply stocking their material locally, delivering it quickly and efficiently on our own fleet of trucks, but to also extend the amount of technical support that's required for them to transition into new materials and processes, similar to the graphene that we're discussing today. So you'll see on the map, we operate out of 44 locations throughout North America, the US and Canada. A number of them have freezer capabilities, so we can service the pre-preg market that we have in North America. And a lot of them also have AS 9120 certification, and that allows us to support our growth in that aerospace market segment. So that's Composites 1 in a nutshell. Let's go ahead and jump into the results. So Paul did a very thorough job of kind of explaining what we did. So I'm just going to give you a quick synopsis real quick. We had 19 samples of different graphene that Vibrance then blended into a BISF slurry, a highly doped BISF slurry. Those samples were then sent to the University of Maine, where we let them down into 0.1% and 0.5% loaded product. We then tested at least 5 specimens of each sample for flexural properties and toughness. Now, you've heard us say it, and I want to emphasize that everything was anonymized. Nobody at Vibrance, nobody at the University of Maine, myself, we didn't know whose product it was. And what that allows us to do is create an unbiased, objective set of data that we can feel confidently stand behind. So let's go ahead and dive deep into the results. So there's a lot of information up here. Probably be beneficial for me to just walk you through what you're seeing there. On the left-hand column, you'll see the 19 samples listed there with the control being the top row. The first set of columns that you have there are the flexural results for both 0.1% and the 0.5% loading. The middle columns are your flexural strength results, and the far right columns are your flexural strain results. You can see we color-coded them, and that allows us to give you a quick analysis of the results. Green is good, red is bad. But I want to take your attention and focus on the 0.1% results of the flexural modules. You'll see samples 9 and 15 through 18 all show green, all show great results in flexural modulus improvement, up to 72%. That's really good. Now let's jump to the flexural strength results for those same samples 9 and 15 through 18. You'll see again we had very good flexural strength results. So that's good. We've got 5 samples now out of the 19 that perform very well in both flexural strength and flexural modulus. But let's jump to the 0.5% loading. So the column for the 0.5% loading, you'll see a lot more green. There's a lot more positive results. But you'll also notice that there's single-digit improvements. So the question is, can we be confident in those results? So it's a good time for us to go ahead and introduce the concept of statistical significance. So I've got 4 graphs up here. All of the data is for a 0.1% loaded material. The upper left-hand graph is our flexural modulus results. Then we've got our flexural stress, flexural strain, and that bottom right is a new set of data that pertains to the toughness. The circles you see, those help us to understand the statistical significance. If the circles are in gray, that means that the results are significantly different from the baseline. So we can be confident that we've got good statistical results. If it's in red, it means that that change in value isn't significant enough for us to see that there's really a change. And so you have to essentially consider them negligible. So if you look at those samples we talked about earlier, sample 9 and 15 through 18, you can see how elevated they are. You can see that the circles are in gray, so we can feel confident that we have good statistical significance in these results. So that's all good. Let me jump you to the bottom right-hand graph. This is our toughness results. If you'll notice, samples 14, 15, 16, and 17 are all in black. The circles are in red. What that tells us, or actually are in gray, what that tells us is that it is statistically significant for those results, but they're in the wrong direction. They made the resin more brittle, so that's not good. But we do have 2 positive results. So you see sample 9 and sample 18 are in red. And what that tells us is that it did not change the toughness of the resin, so we didn't embrittle it too much. So we've got great flexural strength and great flexural modulus improvements, and it didn't embrittle the resin system. So those are 2 very positive results that we quickly focused in and dialed in on. This is the same graph, but for a 0.5% loading. A couple things you notice really quick. In the upper left-hand graph, see how red the circles are and how big they are? What that tells us is that the results we're looking at are not statistically significant from the baseline. So even though we saw a single-digit improvement, there's just too much variability in the results. They didn't perform as well. So that's not good for us. If you jump to the toughness results in the bottom right, you can see they're all gray circles. So we have a big difference, but again, it's in the wrong direction. It embrittles them more. So we could quickly learn that the 0.5% loading did not do as well as the 0.1% loading. There's a lot of reasons why we think that could be, but we wanted to just give a limited attempt at analysis to try to figure out why that is. So Paul's going to jump into the SEM images.
Hi there, it's me again, and I would like to update you on some work we did to investigate, the fracture analysis using an SEM electron microscope. And what we found when we did this, and I'm going to show you this micrograph on the left, is a 200 SEM micrograph of fractured surface area of a neat epoxy resin matrix. This resin matrix has no graphene present. The scale on the lower right of that image is 200 microns. The epoxy coupon was included as a control for our study, and it was subjected to flexural stress and strain. The resulting fracture from the flexural test is largely amorphous, with relatively little disruption to the lines and planes of breakage. Upon successful incorporation of graphene into the resin matrix, as seen on the right-hand side, There is significant gain in properties as indicated by our data. The micrograph on the right is a similar image of a specimen that demonstrated roughly 70% gain in modulus and 35% gain in flexural strength. Note that the lines of fractures are now more distorted, if not more crystalline, and that there are diversions in the stress lines indicative of a fracture. We believe the presence of the graphene is forcing changes in direction of the fracture line, causing the fracture to require a higher level of energy necessary to contribute to breakage. Here we see a 2600x SEM micrograph of a specimen that did not perform well in our testing. The scale on the lower right is 10 microns. Note that we can observe appear to be small aggregates of platelets that are emerging from the surface of the resin in the fracture. It appears that the epoxide polymer may have broken away from the surface of the platelets in this region. We view lack of bonding of resin to graphene as a contributor to failure to gain flexural properties. This phenomenon was not observed in specimens that performed well, even when viewed at even much higher levels of magnification. And for purposes of comparison, we show you a 2000x SEM micrograph of a specimen that performed well in our testing. The scale again on the lower right-hand corner is 10 microns. Note the complete absence of aggregates of platelets that appear to be emerging from the resin in the fracture zone. There are a few platelets that appear to be bedded in the resin and possibly some debris from fractures that may or may not comprise platelets. However, in our evaluation of specimens that performed well in the study, we were not able to find meaningful evidence of either aggregates of platelets nor platelets that had broken away from the resin in the fracture.
So, quick summary of our results. We had 5 good samples that increased flexural modulus and flexural strength. All of that is very good. Then out of those 5 samples, 2 of them did not impact the brittleness, and so we had a very good toughness results from them as well. Again, we want to emphasize this was a blind study. There was no optimization done for any kind of functionalization or any kind of thing like that. So some of those results that did not perform well may have performed much better if we had tried to optimize for the functionalization, but we would have had to lose the anonymity there. In general, the 0.1% performed better than the 0.5%, so that's a good thing for us. And that's the kind of loading we're going to dial into as we go more commercially with this product. I'd like to present what we'd like to do next. So we would like to allow testing of additional graphene materials out there. So if you're out there and you have some graphene that you think would perform well, you can get with Terrence and he can get your product into the University of Maine and get it tested at your cost. We do want to publish these findings in a peer-reviewed periodical, so keep your eyes open for that in the near future. We do want to identify the optimum percolation threshold for specific grades, and 0.1% is better than the 0.5%, but is the 0.1% the optimum loading? Are we better at 0.05? Are we better at 0.2%? We won't know until we do that kind of testing as well. And probably most importantly, we do want to conduct trials in fiber-reinforced systems. So we feel confident that we're going to improve any resin-driven properties like interlaminar shear, things like that. But we just won't know until we test it in a full composite laminate. So that'll be an important next step for us as well. Now, in just simple terms, why is this important? Well, we know we've got a commercial product now that's stronger and better material. It is possible that for your particular application, we may be able to drop a ply stack because of the improved flexural modulus and strength. That could be an incredible savings in weight for certain applications. We do have a cost-effective solution here. So we regularly get pinged by our customers, well, how expensive is it? Well, I could tell you this, at the 0.1% loading, the cost of the graphene is so low that it's very competitive compared to just standard bis-A epoxy resin systems out there. It's a small percentage of your base epoxy resin system. So that's very promising. And then, this is a drop-in solution. There's nothing special you need to do. What we sell you is a graphene-enhanced bis-F slurry that you can just mix into your A side of your epoxy. Nothing special, just the standard shear mixers you're using to blend in your hardener package. So it's simple, easy. You can put it in your production floor tomorrow and not have any issues. So why would you want to work with us? So at the Graphene Council with Terrence, they have an independent and neutral expertise on the supply chain. Really, they're a great resource for all things graphene. They're unbiased. All they care about is promoting graphene in the industry. So they're a great resource for information there. At Vibrance, they've got Paul and a whole technical team that is very experienced in blending various nanoparticles, not just graphene. So they're a great resource as well for understanding the realities and the details of being able to disperse nanoparticles into various resin systems. And then at Composites 1, you have a locally stocked expertise in material where we can partner with you and bring an off-the-shelf item to you to help enhance your product and help transition you into new materials that can really enhance your final product. So with that, we do have some time for questions. We're happy to open up for that. In the meantime, just really want to thank you for the privilege of your time. So any questions out there, just raise your hand and we'll see if we can answer them.
Paul, I would just say as well, if anybody would like a copy of these slides, the statistics, we also have it on our YouTube channel. You have our contact information there, or if you want to see us just immediately after this and give a business card, we can send you a set of the slides. You have all the data that you saw here. You can take it home for further analysis. Do we have any questions? Yes, sir.
Oh, somebody's coming.
Oh, she's got you. She's got
Hello?
Got it.
Yeah. Thanks for a wonderful presentation. I think I'm Sai from Tata Steel, India. I wanted to know whether graphene behaves differently in thermosetting resin and thermoplastic resin. And what's the significant differences? And what is the reason for this inconsistency that you have also observed?
Okay, I'll try to answer that one. First of all, graphene has been used in basically any of the plastics, any of the thermoplastics, and primarily for mechanical properties, but also for, in some cases, to get percolation for electrical conductivity, primarily for anti-static. So we can go from PEEK to nylon, any of the thermoplastics. The reason for the great differences, and it's the reason why graphene is so phenomenal in the first place. You know, graphene is a single atomic layer of carbon, or 2 layers, 3 layers, less than 10 layers of carbon. And what's happening at that atomic level is some quantum effect that gives these extraordinary high electrical conductivity, high thermal conductivity, extreme strength. And the inconsistency of the results is some material is sub 1 micron lateral size, some of it is 5 micron, some of it's graphene oxide, which has a different morphology to it. And this is why it's so critical to work with a graphene either supplier or application development specialist to match the specific type of graphene for what you're trying to do. Graphene is amazing because if I want to improve my barrier properties, I can use graphene. If I want to improve the thermal conductivity, I can use graphene. If I want to do the strength like we were talking about here, I can use graphene. But you need to use the right material that matches the chemistry or the host material that you have. So I don't want to make it sound complicated, but there's a big difference. So this is what the Graphene Council does. We can help educate you about these different things. We have the data, we're neutral, and we can also put you in contact with competent partners, including universities like the University of Manchester, University of Maine, et cetera, and directly with graphene suppliers. I hope I answered your question.
And let me add to that a little bit. For these tests, you asked why is there so much disparity? We also did some microscopy analysis to look at that exact reason, and we tried to explain it in the SEM as well. But all of the samples, even the good performing ones, had a certain level of what I call agglomerations, where the graphene stayed clumped together. But we were able to polarize the images and get an analysis and see that the 0.5% loading had more agglomerations, they were bigger in area, and just spread throughout more evenly. Whereas the higher performing product had less agglomerations and they were smaller in nature. So the theory there is that the better it's dispersed, the better it performs. And that's why we think we saw better results with the 0.1%. I think that why it agglomerated more, there's a lot of reasons for that, the functionalization, things like that. But in general, the better it stays dispersed in the resin system, the better it performs.
Thank you.
You're welcome. Any other questions? I see a hand over there.
Can you hear me?
There we go.
Okay. Hello, everyone. Thank you, Jason, for a very nice speech. I am Mohammad Zaid from Leonardo, and I am associated with this material since last 6 years. this data you said you showed about toughness of these composite materials. Most of the time in literature, graphene is reported as a nanomaterial that enhances fracture toughness of the composite materials. But in your data set, this is in opposite direction. That means the fracture toughness is being reduced. Why is that, in your opinion?
So it can improve the toughness. I'll say this. When it improves the toughness, what happens is that it's very well dispersed, and when that crack impinges on the graphene, it forces a change in the triaxality of the stress, thereby forcing it to have more energy input to continue the crack. So your G1T is better when you have the graphene very well dispersed and it's bonded well into the resin, whether it's an oxidized functionalization or other layers. The 19 samples that we had, 2 of them didn't have any impact on the brittleness, and I believe if we had optimized, really looked at the functionalization, tried to optimize the system for it, we could have improved the toughness. So I do believe that you can get improvements in toughness. It's just very critical for you to understand how well it's bonded into the resin and getting it dispersed in the resin.
Okay. Just one more question.
Sure.
A little curiosity.
I'm sorry. I think we're getting the message. We're,
Oh,
we're
we
out
gotta-
of time.
Okay, we can
Thank you, though.
discuss later.
But please
Thank you.
connect with us. We're here to answer questions, and thank you for your attention. Thank you, Jason.
Yeah, thank you.
Thank you.